Okay, so let's go ahead and get started. Again, the test is on Wednesday, and it's going to cover chapters 1, 2, and 3, including the stuff I'm going to cover tomorrow night. So just be aware of that. I will try to cover it and give you, we're going to do some group work and try to get you on top of that stuff as soon as possible. And then don't forget, I'm going to have lots of office hours. I'll be here tomorrow morning, and afternoon and evening. And then Tuesday as well, I have a review session. I'm going to even be around after the review on Tuesday, so if you don't want to come to the review, but you want to come to my office, Tuesday night I'm going to stay in the office after the review session as long as people want me to, even if it's like midnight or whatever, it's fine. And then of course I'll show up on Wednesday, and aside from stepping in and out just to grab a bite to eat or something, I should be around most of the day. So you're going to be able to see a lot of me. I know I've been hard to reach these last couple of weekends going out of town, but now I'm settled and I'm ready to be settled. So in terms of those 3 chapters, I just want to give you kind of a rough breakdown. Chapter 1, which is on the differential equation stuff, probably going to be about 40% of the test. This is just approximate. And then chapter 2 is maybe about, I put down 35% here. And chapter 3 I put down like approximately 25%. It's all just kind of approximate. And things are, chapters 2 and 3 kind of overlap a little bit. So it's hard to be too specific there. And by the way, just interrupt with questions as we go along. We're not in a rush here. We're happy to take our time and just talk about as much stuff as we want to. Most of the tests, I don't want you to, I haven't written the test yet, but I can tell you right now, I don't like to write tests that involve a lot of memorizing of a lot of different things. So of course I'm going to give you a table of integrals, just like I did for the quiz that you guys took. By the way, you're going to get the homework that you turned in last Wednesday. You're going to get that back tomorrow. The homework you're turning in for tomorrow, you obviously won't have that as you're getting ready for the test. So what I recommend is that you either, if you want to have your own paper to look at, I would take pictures of it before you turn it in. I will post the solutions to those problems, but you won't actually have your own copy. But anyway, yeah, so getting back to this again, I'll give you a table of integrals, and then there are just a few formulas that you really do just need to know. Like, you really want to know these things, otherwise you just can't do these problems. So let me write down a few good formulas to know, and then we're going to start into the actual problems. Okay? That's my game plan, just to get these things down. And I go through these every time I teach the class before the first test to say, you guys need to know these formulas. And there's always a couple people that don't get them down, and it's frustrating because then they can't do the problems. So please don't let yourself be one of the people that doesn't have these formulas down. The first one is you should know the formula for the integrating factor when you're doing linear differential equations. So this is the capital I of x is e to the integral of p of x dx. Don't forget that in the formula for first order linear equations, if there's a minus sign on the p of x term, it has to be part of this integral here. So that's important to keep in mind. Okay, and then the second formula is the Bernoulli Conversion. This actually, I probably should think of this as 2 formulas because there's the change of variables. Okay, this one right here, some boxes around these things. So u is equal to y to the 1 minus n, where what we have is we have the differential equation y prime plus p of x y equals q of x times y to the n. So this is the form of a Bernoulli equation, or at least it has to be representable in that form. Might not be given to you exactly like this, but this is what you want to be looking for. And a linear differential equation is the exact same form, except you don't have the y to the n power on it, right? So this should look pretty familiar. And after I do this change of variables, it makes it into a linear equation, which involves u. So it becomes u prime plus 1 minus n p of x u equals 1 minus n q of x. Yeah, that's right. So just like that. And on the right-hand side, notice that there's no power of the unknown variable anymore. So this one is now linear. The change of variables always turns a Bernoulli equation into a linear equation every single time. That's kind of what you would expect. So you have to know these formulas. Okay, absolutely have to know the conversion, and you have to know what the equation becomes after you incorporate the change of variables. Okay, so Bernoulli equations are very likely for me to ask you that. It was on the quiz, right? And a lot of people did pretty well on it, actually. I graded those myself and felt pretty good about it, but let's just make sure we've still got it down solid, because it's a likely question. One of the reasons I like it, of course, is I not only test the change of variables part, but then you also have to do the linear piece at the end. So I'm kind of testing two things in one problem, which is, something I like to do because it's efficient. Okay. Then there's the homogeneous differential equation. And I just want to make sure everybody remembers the change of variables for that as well. So this is the one where we use y equals xv. And then y prime for that would be xv prime plus v. So just by the product rule. This change of variables will always convert a homogeneous differential equation back into a separable differential equation. And a separable differential equation you solve just by integrating both sides of it. Okay, so remember that homogeneous just means that the derivative y prime, if you solve for it, you get some function where the t's, if you attach t's to the x's and y's, they would just cancel out. Right? So that's what homogeneous means. By the way, there is a problem. Somebody sent me an email. By the way, a lot of good emails are coming in from people with questions as they've been studying, and that's great. Feel free to shoot me emails. In the review problems, I don't know if you guys have all looked at the review problems yet for the exam, but problem number 6, which I don't actually have on me at the moment, turns out that problem is not separable, it's not linear, it's not Bernoulli, and it's not homogeneous. Okay? It's a differential equation that is none of the 4 types that we solved before. So you could say that's probably an unfair question to ask you to solve it. And in fact, I should have given you a hint on that problem. And the student who emailed me about it obviously had looked at the solutions, because it turned out that by using the same substitution that you typically use for homogeneous differential equations, you can solve this particular problem. But when you're going through the review packet, if you get to that problem and you say, oh my gosh, I don't know how to do this, I can tell you don't feel too worried about it, because it really isn't a fair question. I am very, very careful when I write my test questions to make sure that I am very comfortable that they are fair. When I'm writing questions for a packet here or there, sometimes I'm not quite, I still try to be careful, but I occasionally will throw in something that was a little bit off the wall, which is what happened here. So I do apologize for that, but it's not that I couldn't ask you to solve a differential equation that is none of the 4 main types. But if I'm going to ask you to solve a differential equation that's not linear, not Bernoulli, not separable, and not homogeneous, I'm going to have to give you a hint. I'm going to have to say, use such and such substitution, or something of that, or I can't just sort of throw it at you, because that's not fair. That's not testing you on what you learned in the class. So try not to get too freaked out if you see this problem. I just wanted to make that comment. Okay, so far so good? Okay, so those are the main equations about that. Oh, and then I also put down, so number 4 is the last one dealing with chapter 1, which is the Newton's law of cooling. Newton's law of cooling. So there are two formulas here that are both worth keeping track of. The first one is the actual differential equation. The rate of change of the temperature of an object is negatively proportional to the temperature difference T minus Tm. Tm is the temperature of the medium. We took this differential equation and we solved it by separating the variables. We got the big T's on one side and the little t's on the other side when we solved this. And we came up with a full solution. And we did it in class. And you should be able to rederive this. So the one that I'm going to write here is something, this should look familiar to you. The temperature of the object is T sub m plus C2 times e to the negative kT. You can separate variables to go from this differential equation and derive this one here. So this one, the second one here, isn't even in my list really of things you need to memorize. You should be able to derive it. Okay, but you have to know this law first, otherwise you can't do anything. Right? You can't solve it. So I just thought I would mention that one. Okay, does that make sense so far? Okay, great. Let's see, what other formulas? Just a few more things here. The invertible matrix theorem. And now we're moving into chapter 2. Basically, we have done the first 7 bullet points of that theorem. I didn't bring my book with me tonight, but basically it's in the back cover of your book. You're going to find the list. Make sure you know the list. What things are in the list. So the first item is A is invertible. And then the second item is AX equals B. That system has a unique solution for X. Do you have a question?
Yeah. Do we need to know them like conceptually or actually memorize the list?
I think it's worth actually knowing the list. I would recommend that you not have to fumble around to remember the list. So even though, obviously, if you conceptually understand something, it means you're pretty well deeply on top of it. I would recommend it would be good to just, if you're a flashcard kind of guy and you're making flashcards for some of this stuff, I would include some flashcards for the 7 points on this list too. What other points are on this list? An invertible matrix has full rank. So the rank of A is equal to n. That's one of the important ones. An invertible matrix you could row reduce to the identity, right? It's row equivalent to the identity matrix. That was another one of the points. I'm not listing all of them, I'm just giving you some of them. And of course the one we learned most recently is the one about the determinant. A matrix that is invertible will have a non-zero determinant. So you want to know pretty much all of those things, I would say. Okay, so what else do we have here? Number 6. Oh, so I just mentioned the rank. So the rank of a matrix, everybody should know what that is. It's hard for me to imagine a midterm that doesn't require you to understand this concept. This is a big deal. This is the number of pivots. The number of pivots in any row echelon form. Remember that row echelon forms are not unique. 30 different people can get 30 different row echelon forms. But the one thing that all of those different row echelon forms will agree on is the number of pivots. That's just the number of non-zero rows. It's also the number of leading variables. There's several different ways of thinking about it. But for sure you want to know the rank. And if you have an invertible matrix, the rank is the full size n for the n by n matrix. It just means every row and every column has a pivot. They go straight down the main diagonal all the way with no lapses. Okay, so we have that. Couple more things here. Number 7, I have the formula for the inverse of a 2 by 2 matrix would be worth knowing. Just because it's an easy one to be able to apply quickly. So you divide by AD minus BC as a scalar out in front. And then the diagonal entries swap, and the off-diagonal entries pick up a minus sign. So it's just worth memorizing that so that you can use it easily to test stuff. Turns out that, let's see, where do I want to go next with this? Well, let me do the cofactor expansion. I only have a couple more here. Cofactor expansion formula. We did this one last time. This is basically, you can calculate the determinant of A either by expanding a row or by expanding a column. So if you remember from last Wednesday, you're basically going along the rows or columns of a matrix and you're multiplying the entries of that row by the cofactors for that row. Or if you prefer, you can choose a column. Remember, you're usually looking for columns or rows that have a lot of zeros in them. So if you were doing the jth column, the formula would look something like this. Okay? So this is something you haven't had a chance to practice a lot yet. So make sure that you do practice it enough by Wednesday to be really, really comfortable with it. Okay. And then two more formulas. Both of these formulas are on that short video that I did after class on Wednesday. I talked in the video about something called the adjoint of a matrix. Did everybody see that yet? So some of you did, not quite all of you have seen it. The adjoint of the matrix is just simply the transpose of the matrix of cofactors. The matrix of cofactors is just the matrix that you get. Okay, so basically what you do to get the matrix of cofactors, which is written M sub C, you literally just build a new matrix whose entries are the cofactors of the matrix instead of the entries of the matrix itself. So it's a square matrix, and you're just replacing the entries with the cofactors. That's it. And then you have to transpose that to get the adjoint. Right? The sign changes do possibly change in the odd positions of the matrix, but remember that that's already included in the Cij formula. So if there was so this is not a matrix of minors, this is a matrix of cofactors. I've already changed the signs on the odd position entries. Right. So does everybody understand what we're talking about here? I didn't actually do this in our official class, but I did talk about cofactors. And all we're saying here is that you're going to go through and figure out all of these cofactors and just make a matrix out of them. So for example, the 1, 1 cofactor, C11, how do I find that number? Well, if you remember from class on Wednesday, I cross off the first row, the first column of the matrix. I have a submatrix, which is what we call a minor. I find the determinant of that submatrix. And then because it's the 1, 1 position, I don't change the sign of it. I just leave it as is. Okay. If it was in the 1, 2 position or any odd position, once I find the minor, once I evaluate the determinant, I would then have to switch the sign of the result as well. So that's just something else to keep in mind. Okay, so we got that, and then the last and final formula here is A inverse. So we have another formula for A inverse. Besides using the Gauss-Jordan method, we can divide by the determinant of A and then multiply by the adjoint of A. This is also on that video that I didn't get a chance to go over yet. So you just take this matrix here and divide by the determinant. That's it. Actually, let's do something. I'm going to show you something kind of cool here. And then we'll get into the process. So I'm going to show you why formula number 7 is true by using formula 10, which is kind of like the general form. So if I take the matrix, if I take the 2 by 2 matrix, this is just a quick little example just to kind of show you how this would work out, right? 2 by 2 matrix, what is the determinant of a 2 by 2? Do we all have that formula down by now? You had to use it on the homework for tomorrow, right? AD minus BC. So you see, that's on the bottom of the fraction here, which is exactly on the bottom of this formula here. Okay, let's figure out the adjoint of this matrix. So before I figure out the adjoint of it, I'm going to figure out the matrix of cofactors first, which is just another matrix of the same size. If I want the 1, 1 cofactor, I cross off the first row, first column, and I take the determinant of the matrix that's left. What's the determinant of the matrix that's left after you cross off the first row and first column? Just D, right? And do I need to change the sign of that? No, I just leave it as is, right? Okay, what about the 1, 2 cofactor? So I cross off the second column, the first row, and I get a determinant of C, but what do I have to do? Change the sign of it because it's an odd position in the matrix, right? All right, then what about the 2, 1 cofactor? Well, I cross off all these numbers and I get B. It's a 1 by 1 submatrix, right? So the determinant is just the entry itself. It's B, but I have to change the sign of that one as well. Finally, the 2, 2 cofactor, if I cross off row 2 and column 2, I get just A is the only thing left, and I don't have to change the sign of that. Okay? Now what do we need to do to this matrix to get the adjoint? Transpose it. Right, so we just transpose it, which means the first row becomes the first column, and the second row becomes the second column, and look at that. That's exactly the formula in equation 7 there. Right, exactly, that I was looking for. So A inverse then is 1 over AD minus BC times D negative B negative C A. Yeah. The other thing that's really cool about the adjoint method, now I don't want to tell you, oh, well, you don't have to know the Gauss-Jordan method anymore, because sometimes the Gauss-Jordan method is actually better, and I might ask you on the test to use one method or the other, so please be familiar with both methods for finding the inverse of a matrix. But the cool thing about the adjoint method is that oftentimes if there are fractions, in other words, the cool thing about this formula, you know, in the Gauss-Jordan process, you can often get these ugly fractions that show up in the EROs that you're doing and so on. Well, a lot of times in this method, the fraction kind of gets pulled out in front as a constant. It doesn't interact with the entries of this matrix here. So you'll see that if you watch that 10-minute video. I made that point at the end of the video, that the fraction sort of gets factored out. So you're dealing with matrices that usually have whole numbers in them. And that's just cleaner and easier. So especially for 2 by 2, 3 by 3 matrices, this adjoint approach is actually quite nice. Now I have not explained why this formula is true yet. I wanted you to get going on the homework, that's why I gave it to you. But I'm going to explain the formula tomorrow in class, so you guys will be able to understand why it's true. Does that sound like a fair game plan? Okay. So I can't think of really anything else that needs to be like memorized. There's obviously procedure, like general procedures that you need to know. You need to know the procedure for solving linear differential equations and stuff like that. But in terms of just raw formulas to memorize, I think most of what you would want to have on a flashcard, for example, is up here already. Yeah, Sean?
So we don't need to have the formula for the rate of flow problems? Those formulas?
Okay, so the mixing problems?
Yeah.
I said it on my review session sheet, so I'm going to hold true to my promise. I said here that I would give you that differential equation, just because I'm a nice guy. So yeah, so you don't need to memorize that one. The ones about the mixing problems, it's not that hard of a formula, but I guess we'll just call it a freebie. Okay. Okay, so is everybody, any questions about any of these formulas that are up here or anything like that? Pretty good for now? And we'll dive into some problems if you are. Okay, let's I'll start over here. We're going to start with problem number, I'm going to go through this, the questions that are on the review sheet here. I'm going to probably skip one of them because it involves material that I have to cover tomorrow still. But I brought some other ones that we can fill in with. And we'll have plenty to do, I'm sure. Oh, it's nice to be back. Talking about math again. I was working, but I wasn't doing a lot of math the last 3 days. So this is nice. Okay, so here is problem number 1. It's a differential equation. It's going to ask us to solve. So solve 2xy y prime equals 4x squared plus 3y squared. Okay, that's the first problem on the midterm review session questions. Okay. What is the very first question? If you see a differential equation like this, what's the very first question you're going to probably ask yourself? Is it separable, linear, Bernoulli, homogeneous, all that kind of stuff? So, and this is important. You got a little practice with this already on the quiz that you took, but you got to be able to identify these equations properly so that you know which method to use. So looking at this one, does anybody have so maybe you don't know the correct answer yet, but do you have any suggestion? Should we rewrite it somehow? Or what would help us to figure out which kind of equation this is? Yeah, Deshaun?
Well, if you divided both sides by the 2xy, then it looks like it would end up being homogeneous.
Okay, his suggestion is to divide both sides by 2xy. I mean, that's often a useful thing to do anyway. You just isolate the y prime. I mean, when you're looking at homogeneous differential equations, you do have to isolate the y prime. Now, maybe you don't realize it's homogeneous yet. I mean, you could spend some time trying to separate these variables. Of course, when you're separating variables, I usually rewrite it like this, remember? Right? And so I could try to move the dx over here, but the question is now, are you going to be able to get the x by itself on the right side and all the y's on the left side? Algebraically, you cannot do that, right? You're not able to really split this thing up because this plus sign is kind of, if this was all just multiplied together over here and multiplied together here, yeah, we could separate it. But as it stands, the plus sign is really making it algebraically impossible to separate it. Also, you know right away it's not linear. Y squared, right? In a linear equation, you can't have y times y or y prime times y prime or anything like that. It has to just be a very special form to be linear. So it's definitely not linear. So you're kind of looking at it, and looking at Deshaun's point of view is that this makes it look like it's going to be homogeneous. Do you see what's going to happen if you try to attach t's to every single x and every single y? Yeah, see, if I put a t next to every single x and every single y, what will happen is I'm going to get this. And if you start counting how many t's you have, on the bottom there are 2 t's, and on the top there's t squared here and t squared here, which factors out and then cancels the 2 that are on the bottom. It cancels. That's exactly right. So this thing becomes homogeneous. Is everybody comfortable with that? Okay, so and if it's homogeneous, then we know the change of variables that we need to use in order to solve the problem. So let's go through the process. For a homogeneous equation, we have y prime right here. We're going to replace this y prime with x v prime plus v. Okay, equals, and then remember that all you're doing when you're incorporating this change of variables is you're going to take every single y and change it to xv. So the x's stay the same. So the 4x squared, that just stays the same. And the 3y squared just becomes 3xv quantity squared. And then on the bottom we have 2x and then xv multiplying on that. So this is what it's going to look like. Okay? So far so good?